Note card. I want you to do a note card. And so this is going to be, I want you to use a 3x5 index card or cut out a piece of paper that's 3 inches by 5 inches, not 3 feet by 5 feet, 3 inches by 5 inches, okay? And you could put everything you could possibly want on there, right? As many or as few things as you'd like. But what I want you to do is pretend that this is a real quiz. And instead of, you read a problem, and then you flip a couple pages back in the book to like get the formula or whatever, use your note card. Like I said last time, this is a great way to solidify stuff in your head, the actual making of the card, and then to actually use it, I think will be real good for you here. So you're going to turn that note card in with your quiz, okay? So I would like for you to make the card before doing the quiz and then do the quiz. Now, I'm not going to be there to see how you do this. If I were you, if you want to get good at math, what you could do, what I think the best thing to do would be to write down each one of these problems ahead of time. One thing to note is that they're not all the same. Like some of them that are equations, solve the equation. On one section, it'll say solve it on the interval 0 up to 2 pi. And on another section, you're solving stuff, but it doesn't say anything like that. So it wants all infinitely many answers, which we've done this 1,000 times. Your answer should look something like, maybe 7 pi over 6 plus maybe pi n or something like that. That's the form that they want, unless it's explicitly stated, like solve on the interval 0 to 2 pi, then you should have this type of thing. And if you really want to be cool, you could put this type of thing right next to it, though it's not necessary. Okay, so, but what I was saying was if you really wanted to treat this like a quiz that we'd have in class and really get good, I would write each one of these down and like jumble them up, or maybe like write them, find some way to find a random order, like just pick this one, then 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 this one, until you have some mixed up order. Write them all down like on a separate sheet of paper and then do them in that order. Because remember, like I said, when you're in this section, you know which ones you're using. When you're in this section, you know which formulas you're using. But though, you don't have to do that. Like, it's just, if you really wanted to test yourself, that would be a good way of doing it. Getting them mixed up and not knowing exactly which ones, where they came from, that would be a good way of doing it. Though you don't have to do that. Now, I think last time one of you guys said something about, what about checking your work online? Like using, say, Wolfram Alpha to check your answers. If I were you, I would absolutely do that. I started thinking about it, I was like, what would I do? And you're so, I'd do it. I mean, like, And so, you don't have to. I would, if I were you. And one thing I'm going to say on a couple of these, because I did each one of these. If you go check out Wolfram Alpha, you might see some interesting stuff and go, wait a minute, what's that all about? So have fun with that. That's all I'm going to say on that right now.
Both sides of the note card?
Sure, if you want. Both sides is cool. I'm just thinking that the number of things that we have to do, probably won't need both sides, but you're more than welcome to use both sides. That's fine. Although I'm thinking about the note cards I used to make. My writing was so tiny that it's ridiculous. So, like a normal human being writing on a 3x5 note card might need both sides, and that's totally fine. That's totally fine. But do actually use it when you're doing the quiz. And I would suggest that you do the quiz like a real quiz, like you time yourself. And of course, you're going to have you have 2 days to do this, and so like you could wait till last minute to do it, or you can get started right away, and then you'll have even more time to check and go back over stuff. And as we go through, I will say a few things about about each one of the types of problems that I'm going to be looking for. But now, before we begin though, do we have any questions? Especially like over the last homework, or anything from homeworks before? Any questions? Okay, then that brings us to this. So,
Actually,
yeah.
if like if we're like solving for all of the solutions, and then we have two things at the end, and one of them is kind of redundant.
I don't care. That's how, and so like when you see, because I have the solutions I'm going to take pictures of and send to you guys after I collect this, so I'll send that out on Thursday. You'll see that I don't bother to try to figure out a more succinct way of doing it.
Okay.
I just get each one of them, because like, you know where this arises from, right? Like, it usually comes from something like this. You have cosine x, and then you have 1 minus sine x, and then you have maybe 2, no, it would be a 1 plus 2 cosine 2x, all equal to 0. And so then the thing that you do is you go through and you find, okay, where's that equal to 0, and it gives you some set of solutions. You go through and find where that equals 0, and it gives you some set of solutions. You do the same thing here, and now you have 3, just leave it. Like, don't bother to say, well, wait a minute, are some of these redundant? And then try to find a more succinct way of writing it. That's just, I mean, you can if you want. It's just at that point, you run the risk of messing it up, you know? And so I'm not going to be a stickler about that. Just go through and just answer each of those. That's fine. Okay? Everybody good on that?
Yeah.
Okay. All right. Okay. Here's one thing I wanted to talk about, because I started noticing this popping up in homework, and freezes. Let's get it up there. Okay, now, I wanted to do something like this. Okay, so we are going to verify an identity here. And make sure there's not one that I've assigned. Okay, let's see. This is 540. I did not assign this one. Okay, so this is a good one. Cosine. Nope. Bear with me. We want to verify the following identity. Sine 4t equals 4 sine t cosine t times 1 minus 2 sine squared t. Okay, so we're verifying this identity. Now, I'm going to choose one of these sides to start with. And I personally like to start with the more complicated side, though you don't have to. And in fact, I think in this section, both of you guys chose to go from this direction over with at least 1 or 2. I think each of you did. And that's fine. If you'd rather do it that way, that's cool. I prefer to work on the harder side and try to turn it into the simpler side. Whatever. Both ways are fine. So, looking at this, I immediately notice, okay, hold up. That right there makes me think of a... Well, hold on. What did I just say? We're starting with one of the sides. So, I'm going to write that side down. Now that I have this written down, I'm going to write down the side that I'm starting with. And then I'll talk through my reasoning. Sine t, cosine t. 1 minus 2 sine squared t. Now, the first thing I notice is we have a sine cosine together, right? And I know, and in my head I'm thinking, well, we have something that's I know that 2 sine t cosine t equals what? Which one is that? Oh, one of them. It would be on your note card, so don't beat yourself up that this isn't coming straight to your head. Okay. But I believe this one comes out to be sine 2 theta, or 2t rather.
Oh, isn't it? Yeah, sine 2t minus sine.
Yeah, because this one should come from, and remember how we derived each of these, right? This came from sine t plus t is sine t cosine t plus sine t cosine t, which is, yes, indeed, 2 sine t cosine t. Now, notice what I'm doing here. You don't, for these, you absolutely do not need to write all this here. Okay, like, whenever any of those things that you have on your note card, you could just use immediately. Okay, so like, what you could do in this case is go from here, and maybe you want to do it this way. Either way, I mean, you could just jump to the chase, but you could go, 4 is the same thing as 2 times 2 sine t cosine t. 1 minus 2 sine squared t. And then you just jump right to the chase and say, this thing is the same as 2 times this, because it's on your card. You don't need to reference it. This is one thing I'm saying. You don't need to have this written down somewhere. But this is one of the things I want to get into. So we know that this is the same thing as sine 2t. And I don't know if I've just made my life harder or more miserable. I don't know that yet. Maybe it is, maybe it's not. But here's the thing. Oh, and I'm going to copy down the rest so I don't forget this. 1 minus 2 sine squared t. And as I'm doing this, of course, I have my note card out. And so I could see any kind of connections that are happening. This is one of the nice things is having everything on one side of a note card so that you could just look at it and see. Because another one that you'll have on your note card is this. And that turns out to be cosine 2. And on your card it may be written as theta. And this is a point that I'm making here. We know that this is the same thing as 1 minus 2 sine squared t. Theta, sorry. So that's somewhere on your card, right? And you don't need to write that anywhere on the page if you've used it, right? Any of these that are on your note card, you could just apply them immediately. So, for instance, what I'm saying is this is right here, and so you could just jump to this in the next line. That's fine. But if you did, just to make sure, like I don't want to mess this up and I want to actually write it and see it somewhere, you could write it down, and that's fine. One thing that I don't want to see, and you got some comments about this, is having it written right here. Like this right here, this is what I saw on some homework. It looked something like this, but right here in the middle, it had an equals 2 sine t cosine t, and then another equals sine 2t. And it's like, wait a minute, like what this says here is that this entire thing equals this. Like, I know what you're doing. Like, it's just that usually if you're going to use some fact or something like that, you don't want to put that in line of this reasoning, because that's not what that means, right? This says that this line equals this line. And before I'd written this, it said that this line equals this line, which is absolutely right. But then when you throw something like that in there, it makes your poor teacher go, wait, what? Well, I was following you, but where did that? Oh, I see, you're referencing that. So if you're going to do something like that, just put it off to the side, right? Like, and usually you would do it in this, oh man. Wow. Okay, I really have to work hard at this. Yeah, that's good. Much better. All right. Oh man. Need like a hair dryer or something. Okay. Usually what you do is, before you go from this line to this line, if you did want to reference something, you would write it just over here to the right-hand side. And you'd say, okay, so we know that 2 sine theta cosine theta equals sine 2 theta. And so then you're telling the person that's reading this, the reason I jumped from here to here is because of this fact. I've applied this fact right here to jump. This is ridiculous. To jump from this line to this line. Right? Like so in other words, the logic is going like this. This thing is equal to this thing, obviously. This thing is equal to this thing because I'm going through here to get down to here. You don't need the arrows, but that's what that means, right? So it's much better if you're going to reference something, or even I do this sometimes. I'll just write, and you'll notice on the solutions I have some stuff written up over to the sides because I want to make sure I haven't messed something up, you know. And so I just want to see it and go, yes, okay, yes, that's true. So if you want to write it down just to see it, so you could go, yep, yeah, okay, I did it right. That's perfectly fine, but don't put it in line. it's just sloppy, right? And so again, if I wanted to then move from here, I look at my note card and I notice that on my note card there's something written and it says cosine 2 theta is the same thing as 1 minus 2 sine squared theta, theta, right? And if I wanted to write it, I wouldn't write it right here. I'm going to write it over to the side to say that's how I'm getting from this line to this line, which is now 2 sine 2t cosine 2t. Now we're using the same fact one more time. It's that 2 sine of something, cosine of that thing, is sine of double that thing. Double 2t is the same as 4t. So we have sine 4t, which is indeed where I wanted to go. So I am done. Everybody got that? Okay, cool. That was one of the things I wanted to go over. Okay. All right. Give me about 12 minutes to get this off the board. I'm going to erase this. Can I erase this?
Yeah.
Well, may I erase this? We'll see if I can. I'm warm now. That's that's nice.
Do you cut this part out of the video?
No, it's too much work. I don't have the time to cut it out of the video. But it's funny. As I was doing that, I was thinking that. Okay. All right. So now let's see. My fingers are so cold I can't turn pages. Okay. That's super easy. That's pretty easy. One thing you want to keep in mind is that at any time as you're doing these, you may, just because you're in, say, this section, doesn't mean that you might not want to apply some stuff you use in this section. That might come up a few times, right? Or maybe just once. Maybe it won't come up at all. But like, that's something to keep in mind through all of this, is that just because you're in one section and these are the ones that you're using in that section, to get from point A to point B, especially in like one of those prove the identities, or especially in equations where you're solving for some variable, you may want to pull out tricks from other ones too, right? So that might come up. And of course, there's like 20 ways of doing each of these. So just because I did it one way doesn't mean that you're necessarily going to. So maybe you don't run into that. That's all I'm saying. Okay. So one thing to keep in mind is, let's say you're solving equations. And let's do an actual example. Let's say we are doing. Just turn the page. This is so painful. Okay, there it is. So, if we're doing that one. Don't forget that one of the biggest tools in your toolbox is turning something into a quadratic. Okay. Now that may or may not happen with this one, but that's always a tool in your toolbox when you're solving an equation. So we're going to solve for t here, and this is just we're just practicing. We're going to get into this. You'll notice I'm not telling you what section any of these things are from, because, well, that's part of it, right? Like if we were doing this quiz in class, I wouldn't tell you what section this stuff's from. And they're all kind of similar type problems. So what do we have at our disposal that can do this, or that looks like this or something? And so I'm looking at this and I'm thinking, okay.
Are you proving this or solving?
You're solving.
Okay.
You're solving. Solving for t. And this one in particular, like I said, remember, you're going to want to check and double check that if there's an interval, you find the actual ones in the interval. In this case, it says to solve on this interval from 0 up to 2 pi. So, yikes. What do we do with that? What do you want to do with that?
Try to combine, like.
Okay, can we?
Not really. Maybe try to get all of the inputs the same. Like, so it's not t and 4t.
Yeah, I like that. I like that. And so how would we do that?
Just write something in
We
there.
have to use the formula.
There's something.
On our note card.
There's something on your note card, right? So you start looking at your note card,
Is there?
and one thing to notice. Ah, so
We could turn into sines and cosines.
that's, when in doubt. When in doubt, turn everything into sines and cosines. So that's what I'm going to do. I know that there's something with it, like, I know that one of them has like a 2
It's
tan t 1 minus
yeah, that's it.
tan something,
10
right?
squared.
And so maybe there's something there, but then, and so I'm thinking maybe if I divide by this, but then the top doesn't look like that, right? If it were tan t plus tan t, then you'd have a 2 tan t. So maybe, so when in doubt, right? Like nothing's immediately coming to mind. I'm not like, ooh, I see it. Like if it were 2 tan t equals 1 minus tan squared t, then I know I could divide it and I'd be good to go. But that's not the case here. So I'm thinking, when in doubt, let's change these to sines and cosines. So this one's going to be sine t over cosine t minus sine 4t over cosine 4t is equal to 1 plus, and we have 2 of them here, so we have sine 4t, and I'm going to do this all in one. So sine 4t sine t over cosine 4t sine t cosine t. There we go. Okay. So we've changed that into that. Now what do you want to do?
Kill the denominators.
Yeah, why not? right? I mean, I have no idea
Oh,
if
yeah.
that's going to help, but maybe it will, maybe it won't. So what do I need to multiply both sides by in order to kill all the denominators?
Cos of t and cos of 4t.
There we go. Cosine of t and cosine of 4t on both sides here. So cosine t, cosine 4t. Now, that guy jumps over, kills that, leaving me, how about a sine t cosine 4t. Jumps over there, I have a minus sign between them. Jumps over, kills the 4t, leaving me a sine 4t. Cosine just 1t now. And that looks familiar. This guy jumps over, and the first time when he jumps over, jumps over all the way to the left, nobody's killed. He's just cosine t, cosine 4t. Then we have a plus. Kills the entire thing, leaving me plus sine 4t. Or how about sine t, sine 4t?
Yeah, that looks cool.
That looks nice. So this looks very familiar now. What is this?
Sine of
Sine. So yeah, this goes into sine of something.
t minus 14. Wait.
Sine's the same, so it should be
5t.
minus. Wait a second. Minus t and 4t. So there's the t
Alright.
and the 4t. Now, did we do that right?
Yeah.
Or is it 4t minus t? Well, if you remember the way we've done it in class,
Sine.
the way we've set it up is that you go sine cos, sine cos. If there's a minus in between, there's a minus there. And the way we've done it is that the first sine is the first thing. Okay? So that is correct. That is right. Now,
Cosine.
this is going to be cosine of stuff.
Maybe t minus 14.
T minus 4t. Because cosine is the opposite sign, SIG in sine. And the way we've set it up is, but actually cosine can go either way. Because it doesn't matter,
Yeah.
right? If you swap those around, it's the same thing. So, but I'm going to choose to do it this way because that one's that way. And so we have sine of negative 3t is equal to cosine of negative 3t. Now, if we want, we could get rid of those negatives.
Could take them out.
So if I take it out of the cosine, what happens to cosine?
It
Nothing.
becomes positive.
Just goes away.
It just goes away. If I take it out of sine,
Negative sign.
negative sine 3t. Now what do we do?
Minus the cosine. Or add the sine, doesn't matter.
Add the sign.
One way of doing it. You could. You could.
Wait, no, we just divide by cos and we have sine over cos.
You see, that's
Oh.
that's what my intuition tells me is that I could just divide. I'll have sine of something over cosine of the same thing. Now, it would be different if it were 3t and 2t, then we couldn't do that. But since it's the same thing, we could take this step where we say, well, I'll divide, and now I have negative
But isn't that
sine 3t over
assuming that
cosine
it couldn't be 0?
3t. Uh-huh! Yes. And when you do that, let's make a note. This is assuming that cosine 3t is not 0. So we're going to have to, and I like to make that note there so that when I think I'm all done, I go back and go, let's take care of the case where it is 0. And we have to figure out, okay, when that is 0, is that thing ever 0? And we'll go into that in just a second. But for right now, this is good. The whole reason we did that is because that we know that sine divided by cosine is tangent. So this gives us negative tan 3t is equal to 1. Or how about tan 3t is equal to negative 1? So let's do a substitution. Let's do theta equals 3t, so that tan theta is equal to -1. And what I want to do is see what's going on. And so I'm going to graph tangent theta, and like now we're talking about a compression, and so really, yeah, well, you know what I'm saying? So like, even if we find them all where theta is between 0 and 2 pi, doesn't mean that we got all of them. So we got to be careful here because we're graphing theta, right? And so here's pi over 2. Here's pi. There's 3 pi over 2. There's 2 pi, and so on and so forth, right? And so now I'm going to think, okay, -1 is down there. So there's one back there. There's one there. When does tangent give you a 1?
Pi over 4.
There you go. Yeah, good. Good. You guys are getting this. Okay. Right. When it's pi over 4, tangent is 1 over 1. So we're talking about pi over 4 is the reference angle here. So we have, here's pi over 2. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and all of those. So those are all those. There's my
3.
Must be 3 pi over 4. Okay, and then not 5 pi over 4, but 7 pi, because this is 3 pi over 2, right? But one thing to notice is like these are all going to be off by how much? What's the distance from here to here? What?
Pi over 2. Wait, distance from where?
Oh, I'm sorry. From between the zeros.
Oh,
From
pi.
here to here. It's off by pi because tangent is periodic with pi, right? Its period is pi. And so we could write this succinctly by, we just need to find one of them. We found one of them. We could use that one if we wanted, but we found one. 3 pi over 4. So in other words, when theta is equal to 3 pi over 4 plus, not 2 pi n, pi n in this case. And yeah, that actually makes sense because 3 pi over 4, add another pi, where do you end up? 7 pi over 4, and so on and so forth, right? So, okay, but we didn't care about theta, we cared about t. And so theta is 3t, so I'm going to go ahead and go 3t equals 3 pi over 4 plus pi n. Getting the the t by itself, I'm going to divide through by 3. And that gives me, this is going to look ugly, t equals, the 3 kills the 3, we have pi over 4 plus pi over 3 n. Okay, but now we need to find, and again, this does not, oh, we have them all. No, we don't, because now we're talking about this t is in this interval. This is when theta was in that interval. It's not the same thing, as you'll see, right? So what I'm going to do, and this is, you'll notice that this is, when you see my answers, this is how I've written this. Now, here's one thing to notice, actually, I wanted to talk about real quick. Is that back here, we also have a formula, like later on, this is, I'll come clean, this is from the first section where you're using this, right? But if you didn't know that, you might think this is from the most recent section that you've done. In fact, that's probably why your mind immediately went to, well, add it to the other side, and then you could combine and get the thing. And that would work, and you probably could, you certainly could go that way. Is that going to help? Maybe. Is it going to be any harder, easier? Probably not. It would probably end up doing about the same thing. Okay? So, but my point is, like, any of these can come up at any point. And you, if you have a way of not using one, you could do that. If you wanted to do the thing from the last your most recent homework, the what's it called, sum to product formula, you could use that too, and you'd end up with the same thing. So it's up to you. Okay, so let's find the ones that are actually in 0 to 2 pi. So, like I was saying, when you see my solutions, what I've done is when I would get down to a point like this, I just started listing these things out, like just under it. I would say, okay, well the first one is when n equals 0, and I did this above it so that you could decipher what I was doing. I was saying, okay, when n equals 0, we'd have pi over 4. And when n equals 1, we'd have, this is where I'm going to convert this over here. I'm going to say 12, we need a 12, so that would be 3 pi over 12 plus 4 pi over 12.
7 pi.
Okay, so when n equals 1, yes, 7 pi over 12. When n equals 2, we have 4, 5, 6, 7, 8 pi over 12.
So 11. Oh, wait, yeah.
Right? When n equals 3, we add another 4, 8, 9, 10, 11, 12 pi over 12. I'll just write it like that. Who cares? 12 pi over 12. When n equals 4, we have 16 pi over 12. When n equals 5, we have 16, 17, 18, 19, 20 pi over 12.
And you can
n
do
equals
one.
6
You can do one.
is
Oh, yeah.
24 pi over 12. So that one actually works, but that's actually, it's not included.
Oh.
That's not 12, right? That would be 2 pi over 12. And so then I wrote too far, or too big, I think, is what I wrote. Too big, okay? And so I'm not going to use that one. Because notice, we're not including the 2 pi.
Yeah.
Is everybody with me? 24 pi divided by 12. This is the same thing as 2 pi. And so we're not including the 2 pi, so we don't need to answer it. But let's just make sure that we can't go the other way. Because remember, n is not just positive numbers. And remember what we originally drew? I drew a tangent thing, and it stretched off this way. It also stretches off this way. So we need to check the negative integers too. Okay? So I'm going to say when n equals -1, that would be 3 pi over 12 minus 4 pi over 12 for a minus pi over 12. But that's outside of my bound too, so that's too small. And so these are the answers right there.
Do we have to check the 0? Like,
Yes, thank you. So those are the answers, and I think, okay, I'm all done. Uh-oh. What happens there? Well, let's try to think about when is cosine. So all of this assumes that since I divided by this guy is not equal to 0, but what if he is? And so what I'm going to say is now, let's figure out where cosine 3t is 0. And it's the same kind of thing. I'm going to say, well, when is cosine theta equal to 0? And I just think about this. Okay, here pi over 2 and 3 pi over 2. And then plus and minus 2 pi. So either theta is equal to pi over 2 plus 2 pi n, or theta is equal to 3 pi over 2. So then theta is equal to 3 pi over 2 over 2 pi n, or plus 3 pi over 2 plus 2 pi n. Substitute my 3t back in, just saving space here, 3t. And so we get that t is equal to pi over 6 plus 2 pi over 3n, or t is equal to pi over 2 plus 2 pi over 3n. Now we need to figure this out. Is this thing, well, you know what we could have done. Because what we're asking, is this ever going to be true? If this guy is equal to 0, right, is it ever going to be the case that that guy is simultaneously equal to 0? And now I've just made my life way harder by getting out of the thetas and into the t's. One thing to notice is that I could have said, well, wait a second. Because now I have a bunch of things to check and I'd have to plug them in. Or I could just say, well, wait a second. Is it ever the case that cosine of theta and that guy are equal to 0 at the same place? When is cosine theta? I don't think it ever is, quite frankly. Because is it ever the case that sine theta is equal to 0 here or here?
No.
No. They're never equal 0 at the same place.
So you can't.
And so that won't be a solution. So we don't need to worry about it. One thing we haven't talked about. One thing we haven't talked about. So, like all bets are off if you divide by 0. All bets are also off if you multiply by infinity. So if you say multiply both sides of equation by tangent, there's a place where tangent's equal to infinity. And all bets are off.
Oh, yeah.
You know what I'm saying? And so, because let's say you have some equation. Well, that's not true. But if you take it and multiply both sides by infinity, you get something that's true. And so it's like another one of those things, like you can't really do this, and so things pop out. But we haven't talked about that, and if you miss it, I'm not going to count it off, because we've never talked about
So
it.
you can't multiply both sides because of the pi over 2.
Well, yeah, so I'm just saying if you have some kind of equation here, right? And let's say that this were over... Let's just say that this were the equation, that it looked like this. Okay, I'll just cram it in there. And let's say we had a tan t right here. And I'm not going to try to do whatever. I just want to go from here to the next step, which is that sine of whatever is equal to tan t cosine stuff, right? I'd have to think, am I multiplying by infinity? Well, there is a case where I am multiplying by infinity, and that's if tan is pi over 2 or 3 pi over 2 or stuff like that. And then you'd have to reconsider. The same way that we got a bunch of answers, everything was cool, but there's this place where it might have been a problem. And then we found out it's actually not a problem because sine and cosine can't both be 0 at the same time.
So you're assuming that t can't equal pi over 2 or something.
So you'd have to, so you're implicitly assuming that t is not equal to pi over 2 plus pi times n. And if it were, then maybe something else happens, but we haven't talked about that, and who cares? It really, it's just one of those things that's good to know. But I mean, if this were it, the cosine would kill the cosine that's sine over cosine, and so, yeah, I'm just saying, don't worry about it. Yeah. It's something to know that it happens. It rarely, if ever, causes a problem. And so, it's just something to notice. So, let's see. Yeah, so in this case, we just needed to check that, okay, but all of this assumed that cosine 3t was not equal to 0. What happens if it is? Well, we still don't get equality over here. It's still not equal back where we first took this step. So we don't need to worry about it. There are no more solutions. These are the only solutions. That's my answer. We are done. We good?
Yeah.
Okay. Now, since you have tons of time for this, you probably want to go through and just check these answers. I would. I would just plug them in here, right? And you could do that really easily, in Wolfram Alpha, is you could put this equals this, comma, t equals that. And you just check, and it'll check it, and it'll say that there's one solution, and that, yeah. Because it treats it like two separate equations. It's saying solve this system of equations. This, and the fact that t equals that. And if it's not an answer, it'll say no solution. And so then that way, when you're done with that, you just go back up to the bar and change one thing. Instead of having to put this into each one of these each time, you just change your t equals whatever to each one of these. And So, okay. Now, what else was there? Those. I talked about everything I wanted to talk about. So, could just do a couple more examples. Yeah. That's good. This is gonna be such a pain.
Flip the whiteboard.
What?
You could flip the whiteboard.
I
I guess you still have to erase
But
it.
then I'm leaving it for the next person. They're gonna have to sit there and go, what's a cost?
Has to be some kind of solution. How do we?
What now? Oh, for this?
Yeah.
I was like, we just found the solution, Noah! Where have you been? Yeah. So, this is gonna take me like 5 minutes. Why don't... I don't know if you do you have your book with you?
No.
No, then here, Noah goes first. You find something in the sections that we're talking about. Not one of these, but look and find something. Or like perhaps look back over these because you've done homeworks from each one of these. And if you want to look and say, oh, this was something, I had a problem with this or whatever, just use that to... Broke my eraser. Yeah, that's good enough. Good enough for government work. Okay. Okay, do we have something?
Wait, were we supposed to start doing it? Or-
No,
Oh.
like we're supposed to talk about something.
Oh.
Yeah, I have one.
Okay, what do you have?
Number 70.
Ooh, okay. Destructive interference.
Was that one of the application?
It's one of the application problems. Refer to exercise 69. Okay.
Yeah, this was one of the ones I did. Which ones did I do? There was one about violin strings.
Oh yeah, I did that one.
Okay. Let's get some of this on the board.
And then,
So,
I don't remember.
A.
I tried the gutter one, but it was too hard.
Okay, so the tuning fork is struck
Oh, it is.
and held. So I'm right now reading. It says refer to exercise 69. So I'm reading from exercise 69, and I'm going to get the information from it. So it says if a tuning fork is struck and then held a certain distance from the eardrum, the pressure P of T. The pressure on the outside of the eardrum at time t may be represented by P of t equals A sine omega t. And it looks like a W, it's omega t, where A and omega are positive constants. Let's think about what that means, right? The pressure, so how much pressure, if you wanted to graph pressure versus time, it would be something like this, right? Where A, they're using A because that's amplitude, the max pressure, and then omega would have something to do with the period, right? Which we could find by doing 2 pi over omega would be the period, right? So the bigger omega is, the faster this thing goes, right? So like if we're talking about A at 440 hertz, 440 hertz would be 440 cycles per second, right? You guys are both musicians, you know 440, right? And so if that were the frequency, you'd have what, 2 pi over omega, right? So then omega would be 2 pi over 440 or something like that. Or no, that's not it. That's not how it works. I messed that up. I messed that up. It's 440 times 2 pi. If omega is 440 over 2 pi, then because I'm talking about period. And frequency is 1 over the period. So then, yes.
Okay.
Right, because frequency is 1 over period, and here your period would be 2 pi divided by omega, which would be 2 pi divided by 440 times 2 pi. The 2 pi's cancel, and you have that your period is 1 over 440, 1 over 440, your frequency would be 440. Yeah. Anyway, okay, so this is what's going on. It tells us that the positive constant. If a second identical tuning fork is struck, possibly with a different force, and held a different distance from the eardrum, its effect may be represented by the equation, and they gave this a little, there's a P1, they gave us a P2 of t, is equal to B sine omega t plus tau.
Is that a letter? Oh.
It's a Greek letter, tau.
So is it just a constant?
Just another constant. And it doesn't say positive constant, where B is a positive constant, and tau, this one's 0 to 2 pi. So let's think about that. Say, struck possibly at with a different strength, right? Or possibly with a different force. So if it's struck with a harder force, B is going to be bigger, right? Because the B here represents the amplitude, right? And if it's struck harder, then it's going to have a higher amplitude. Notice that omega is the same, because it says an identical tuning fork. If your tuning fork is A440, it will vibrate this much no matter how hard it's struck, Okay, they always, well, close enough. It vibrates at a certain frequency. It has a resonant frequency that's determined by the material itself. That just changes its phase a little bit, right? So it's the same. So B may be bigger, let's say it is, and it might, and so it's going to go, it'll have the same frequency, but maybe it's been offset a little bit, right? That's what tau does from 0 to 2 pi. Because you've done it at a different time, and so it's vibrating at different whatevers, and so maybe it's...
Why does it have to be from 0 to 2?
Because it would be redundant otherwise, right? Like, after you move it past 2 pi, well, now you've just repeated it. And so it's saying it can be described by a tau that's between these two. Even if it were off by in actuality, you did this 3 seconds later or 5,000 seconds later. In reality, your actual shift may have occurred much later or sooner, whatever. But we could always reduce it down to something here and here. So that's what that's saying. Okay. The total pressure on the eardrum is given by the sum of these two. A sine omega t plus B sine omega t plus tau. Okay? So show that that one of those, that it can be rewritten in a certain way, and then show that the amplitude is that and that. Okay, so we've referred to exercise 69. Destructive interference occurs if the amplitude of the resulting sound wave is less than A. Okay, so 1 second. So one thing that we didn't talk about was it says show that the amplitude C of this. So the amplitude, when you add these things together, is what it's saying. Then the amplitude of this, one of the things, we're going to call that C. And it says show that that has this property right here.
Looks familiar. Oh.
Mm-hmm.
Oh. So in that there.
Wait.
So we can use the
Let's do it.
the sum thing to make it so,
So-
they're multiply.
The first thing it says to do is show that P of t equals... So this is our goal. The first exercise says show that P of t, that is the combined P1 plus P2, show that P of t equals A cosine omega t plus B sine
Well,
omega t, where A is equal to B sine tau,
big.
big B sine tau, and little b is equal to A plus B cosine tau. Okay. Okay. All right. First thing I notice is we have a sum. Omega t sine of something plus something.
Oh.
And I'm thinking maybe we could use that to get maybe something like this to pop out. I don't know. Let's just see. I'm going to take this and say, okay, this is the same as A. Notice this is what I'm going off of. Sine omega t plus B times, and now I'm going to rewrite this as sine cosine plus sine is the same, so plus sine cosine. Now we have omega t tau omega t. Now I'm going to look back here and C. Oh yeah. Look what they're saying. That we could write this as something times the cosine part, something times the sine part. And now I'm seeing we have a sine part, cosine part. So maybe if I just rearrange the stuff, all of this will happen. I don't know. Let's find out. A sine omega t plus. Now I'm going to distribute my b. B sine omega t cosine tau plus b sine tau cosine omega t. Now let's just group all of the sine t's together. And I get that would be, so I'm going to go ahead and just factor out that sine omega t.
Yeah.
And what will be left is my a plus b cosine tau all times sine omega t.
Wait. Oh
Yeah?
yeah. Yeah.
Yeah? And then this guy is b sine tau cosine omega t and a cosine, there we go, there's that, I've shown it, right?
Yeah.
Because this says that this has the form some number times cosine omega t, some number cosine omega t, where that number is that number's that. This is plus some number times sine omega t. There's sine omega t. There's some number, and that number happens to be that. Okay, we've done it. Now, here's the hard part. Finding the amplitude of this guy. Okay, how are we going to do that? How are we going to do that? Well, so that's P of t. We've just shown that P of t is that right there. Show that the amplitude, when we come back Thursday, we're going to learn, you're going to see this actually. So I'm trying to think of how to do it without doing what we're doing. See, I already know where we're going with this, and now I'm thinking, how would we do this if you guys don't know that? And so let's think about this. The amplitude of that, well, here's something to notice. This is okay, so each one of these are constants, right? A is a constant, B is a constant. Tau is a constant, therefore cosine tau is a constant. That constant's also between 1 and -1. Sine tau is a constant. So really, like this could be something like a plus b times a half. And this could be b times √3/2 or something like that, right? So again, now let's just do this. Let's actually simplify it. We're going to do these substitutions for a minute and say, yeah, because those are constants. For any given tau, any given a, any given b, this is just some constant. A sine omega t plus b. I want to keep those right. That's my b. I should have used my hand to erase this. That's ridiculous.
Because your hand's warm.
I guess so. Okay, so yeah, that must be it. And there's probably oils on it, Okay, so now what I need to do is figure out how do we find a magnitude of that? How do we find the magnitude of something like
Well, we
that?
could
Well, what's your idea?
write it as a product instead of this.
Yeah, I'm thinking that, but then we got these guys out front, which I don't know how to deal with that. So give us any other hints. Show that the amplitude of that is given by that. Huh. Amplitude of that is given by that. Ooh. If we did, it'd be easy if we could just do some calculus, but we can't do calculus in this class. It would actually be really easy in this class.
We should do the calculus.
Can't do it. I can't remove the veil just yet. But let's think about this. If, ooh, actually, the max that ever gets is this.
Well, we know.
So,
We could. No. It's hard.
Take a log of both sides.
see, if we knew that the max, that P, if we could just find the maximum value that P takes on, because it hasn't been shifted up or down, we would have the amplitude, right? Because like, look at this, right? If you add these things together, and let's say that when you add them together, you get something up here, C, and that's the max that it ever gets. If you knew that, and you knew that value was the maximum value, you would know its amplitude.
Yeah.
With calculus, you could find that very easily. But I'm like, well, oh yeah, and then you get that and you get that. But we can't do that. So I'm thinking, what are they trying to get us to do instead? So
Rewrite the cosine as sine of WT minus pi over 2.
oh, here it is.
Oh.
Here it is.
Why not?
This is they do an example. There's an example in the book where they show, and so this is in the book. This would take too long to actually do, but it's in your book on page 529 if you want to take a look at it. They show that everything that has this form can be rewritten
Oh.
in the following way as A cosine B, not the same A, we're gonna get to that. A cosine BX minus C, where A is equal to that, the square root of this squared plus that squared. Tan C, yeah, right? Tangent of C is equal to B over A. Yeah. And C is between negative pi over 2 and pi over 2. So, but we don't care about that. All we care about is the amplitude, because that's the idea. And so, you could take a look at that, how they go through and derive that. It's not that hard, but it's in the book. So that's how you're supposed to do this one. Sometimes they just have a random example that gives you how to get from one thing to another. That's the thing. So now that we have that, and that actually it does make a lot of sense. Okay. So anyway, so since that's the case, the amplitude of this new thing, which can be rewritten as a cosine, one single cosine, and its amplitude is given by the square root of that squared plus that squared, and we know that that is that and that is that. Let's just do that. Its new amplitude, so there's a prime for A, it's not the same A, it's a new A, is equal to the square root of that squared, so A plus B, I'm just going to write cosine, and we know that it's cosine tau, plus B sine tau squared, which comes out to be the square root of that first outer interlast gives me A squared, plus 2 AB cosine, plus B squared sine squared.
Oh, cosine. Oh yeah. Wait, wouldn't it be
Oh,
cosine?
b squared cosine squared. This is plus b squared sine squared. B squared sine squared, pull out the b squared. Pull out that, right, and we would just have a b squared, right? Pull out the b squared and you have cosine squared plus sine squared, which is just 1, so it's gone.
Yeah.
This is the same thing as a plus b quantity squared. Yeah?
Yes. Yeah, it is.
Oh, ooh.
Wait.
Oh, the cosine.
Cosine.
Wait, what?
Yeah. Wait. A plus b cosine, take it and square it. B sine, take it and square it. That gives you first, outer is ab cosine, inner is ab cosine for a total of 2 ab cosines. B squared cosine squared, got it. B squared sine squared, got it. You pull out the b, leaving you cosine and sine, which is just 1, leaving you just a b squared. That's what that is.
Oh, you know that's right. Yeah.
And we're trying to show that it's equal to that. Oh, c squared. Yeah. So this was, there's your amplitude. That's it.
Oh.
That's your amplitude. But that's not what they asked us to show. They asked us to show that amplitude squared. Square it and you get a squared plus that stuff. But how about b squared first? Then plus 2ab cosine.
So we did tau.
There's that. We did. Ugh. Okay, from there, right
Is this one of
now.
the ones you did?
So that was all just that first problem.
Goodness.
Okay, I know we're like way late, but now it says refer to exercise 69. We checked it. If the amplitude of the resulting sound wave is less than A, suppose that the two tuning forks destructive interference occurs if the amplitude, the new amplitude is less than A. Okay, so in other words, the only way that's going to happen, I'm thinking it has to have something to do with this being a negative number. Right? Because if that's a positive number, then this is a positive number, and you're adding to the amplitude. It's going to have to be that you've subtracted from that. Right? So like for instance, if A is 3, then you have 9, and if B is 2, you have 4, and then you have plus 2 times 3 times 2 is 4 times 3 is what, 12?
Yeah.
12. And then you have cosine tau.
And
9, 10, 11, 12, 13. So you have 13 plus 12 cosine tau, for instance. Then it's going to depend, because if tau is -1, right? Like, I mean, if cosine tau is -1, which would happen if tau is at pi, so in other words, if they're perfectly out of phase, then this thing gets as small as possible. So that's a -12. And so you have 13 minus 12 is 1. And so then that amplitude, the new amplitude here, the new amplitude would be smaller than A. That's the kind of thing they're talking about. That's destructive interference, where instead of making it bigger, it actually makes it smaller. It says, suppose that the two tuning forks are struck with the same force. That is A equals B.
yeah.
Okay. So then we have, in other words, A squared plus A squared would be 2A squared plus 2A squared
You can factor out.
cosine tau. And so we have the 2A squared 1 plus cosine tau. Okay, that's what it says. Suppose that they're the same. When total destructive interference occurs, the amplitude is 0 and no sound is heard. Find the least positive
Wait,
value for which this occurs.
Does that really happen?
Okay, so then if C is your square root of that stuff, which is 2a squared 1 minus cosine tau,
One
when can that ever be 0?
wouldn't it be 1 plus cosine.
Thank you.
What
Thank you.
is
Good.
What is that?
Is the only way to multiply by something and turn it into 0 is if that thing's 0.
Yeah.
Total destructive
Okay,
interference would occur. And so 1 plus cosine. In other words, we know that cosine tau would have to be -1. It's the only way you're going to get that thing to be a 0. That's going to occur when tau is pi. And they're exactly out of phase.
And then you hear no sound. Wait,
And you would hear no sound.
that's weird.
Yeah, it'd have to be out of phase by pi.
That's so weird.
Determine the interval, the tau interval, for which the interference occurs and A has its least positive. Okay, so then you're looking for, assuming that those things are the same. So did everybody get that? Like how we got to there? I'm sorry, this is such a jumble. But did everybody see how we got that?
Yeah.
Did that make sense?
Yeah.
Okay, like right, we're assuming that the two forces are the same and therefore the amplitudes are the same, so it reduces down to this nice little thing. Now it says find the interval for which destructive interference occurs. And destructive interference would be where you end up getting something that's less than the original, right? So your resulting amplitude is less than A. So then what you're doing is you're solving when is C less than A. And so, C, I'm trying to find room here. You're saying when is C
Right over.
less than A? But we know that C is equal to that. So root 2a squared 1 plus cosine tau is less than A. Square both sides, and we could say, assuming that's positive, which it's going to have to be. You can't have in this case, you're not going to have a negative amplitude.
What is a negative amplitude?
Yeah. So squaring both sides, we get 2a squared 1 plus cosine tau less than a squared. The a squareds are gone, and we have 1 plus cosine tau less than 1. Divide through, and you have 1 plus cosine tau less than 1/2. Subtract off a 1, and you have cosine tau less than 1/2 minus 1 is negative 1/2. Negative 1/2. And so we just need to find out where it's less than negative 1/2. Cosine, graphing that against tau, negative 1/2 occurs
Pi over 6? No, pi over 3.
pi over 3, I think, right? Pi over 3, 1, and 2. So yeah, negative 1/2. So it would be pi over 3. So wait, in which quadrant? Pi over 3, 3 pi. So pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, and 5 pi over 3. So between 4 pi over 3 and 5 pi over 3.
Yeah.
That's when it should occur. Unless I messed something up, which I probably did because there's an inequality and yeah. So I hope that was fun. I hope that kind of demystifies some stuff. But yeah, it's like the waves will cancel each other out. And you can see this if you drop pebbles in a lake or something or in a pool, right? You can see sometimes the waves will add up with each other. And you could do this. I would suggest go on Desmos and play around with this. Like write a P1 and a P2 and put them together, and then use sliders to see what we're talking about. Use a slider for tau and use a slider for A and B.
And
And you'll see that depending on your phase, you can make it small. You can make the resulting amplitude smaller. Because if they're out of phase from each other and you're adding them together, right?
yeah.
So like if this is, say, your P1, and let's say your P2 is just barely out of phase, right? It's just ahead or lagging behind, right? Then you could see, like, if we're going up to 1 here, well, this is almost 1 plus almost 1 right there. And so that's going to be a big number. This is almost -1 plus almost -1, so it's going to be almost -2. So your resulting bit's going to get bigger, right? But if you pull that out of phase even more, you can see that there's a place where it's going to exactly cancel out.
Yeah.
Right? So if you pull it off by pi, see what's happening here? If you stretch, or if you pull that out of phase by pi, well, then you're here at 0 plus 0 is 0. And then you're here at 1/2 plus minus 1/2 is 0. You're here at 1 plus minus 1 is 0. And so that would be destructive interference.
So then if you drop 2 pebbles in water at the same time, there might just be the
Well, it
waves might
depends,
just
and it
go
would
away.
depend on how far apart they are, because how far apart they are determines the phase,
Yeah.
right? And also, they would have to be exactly the same weight, drop from exactly the same height, and so on and so forth. And the water would have to be perfectly straight. But that does happen, and in like quantum mechanics, this happens a lot. You have what's called an interference pattern. So if you fire 2 photons through two, it's called the double slit experiment. So if you, let's say I put a big slit right here in the board, and I put a slit right here in the board, and we're firing photons through them. Like these photons, they kind of make waves, and these waves there'll be constructive interference where they come through. I wish I could. You know what? Yeah, whatever.
You can just look.
I could, but
Yeah.
I'm not gonna. So, if you imagine, we're gonna look down at a wall, and we made 2 slits in this wall. And through these slits, photons can go out. But photons aren't particles, and they're not waves. They're kind of both. And what happens is they make these waves as they go through, something like this. Right, so as a photon travels through, it makes waves, much like waves rippling so what I'm kind of drawing is the peaks, right? There's a peak in a valley, another peak, and another valley, another peak, right? So if you're looking at it like this, right, and like if this were water and I dropped a pebble, you would see waves, radiating out. Photons do the same thing. And when you fire a photon through here, it also does that. But there are places here, as you can see, that these waves are going to interfere with each other. And where 2 peaks meet each other, it's going to get bigger. But where a peak and a trough meet, it's going to cancel out. And so what happens is if you just take a light, and you could do this, you just take a light, shine it through 2 slits. Hey, sorry, somebody asked me about waves, and so here we are. And so you shine it through 2 slits. The places that constructively interfere, that means that the peaks where they get bigger, you will see a band of light. But the places where they destructively interfere, where one peak is high and the other one is low, where they're out of phase, then you will not see any light. But then you'll see a pattern. And depending on how far apart these are, you'll see these, what's called an interference pattern. You'll have bands of light on the wall. And so it's a wild world out there. But you could see the same kind of thing like if you were to drop 2 pebbles. Right. If I drop 2 pebbles in a pool and I looked at how the waves hit on the walls back there, there would be places where the waves got really high, that is where the different waves came together at a high, where they both had a high point, and then they came up really high on the wall. And then you'd see places where it's just flat. that's where one wave was coming up and one wave was going down, and so they deconstructively interfered.